All right, so I think last time we only got to alpha decay, and we reviewed that an alpha particle is the same thing as a helium nucleus, and when we write decay equations, we might see the alpha particle sometimes, we might see just the symbol for helium sometimes, right? Same thing. And I think we looked at maybe 2 examples of an alpha decay. So you'll see some more in a few minutes in your foursomes. I'm already recording, right? Great. All right, so our next type of decay is called beta decay. And why is it called that? No, they're just all named after the first 3 letters in the Greek alphabet, right? Alpha is the first letter, beta is the second letter, gamma is the third letter, right? There's no good reason that it's called beta decay. So an alpha particle is the same thing as the helium nucleus. Well, a beta particle is the same thing as an electron. Right? So it's something we're even more familiar with than an alpha particle. And beta decay can be treated very simply, which we'll do at first, but then there's really much more to the story, which we'll account for as well. So a beta particle, if something does beta decay, gets emitted from a nucleus. So here, we're starting with the nucleus. Oh, what element is that? Hydrogen, right? H stands for hydrogen, we all know that. And there's 1 red thing and 2 blue things. So what's a red thing supposed to be? Proton. Yeah. So we have hydrogen 3. So we're going to do our kind of chemical inventory for this. So we have a proton number of 1, a nucleon number of 3. Just like alpha decay, we only have a single reactant, right? We don't ever have 2 reactants. Well, for natural radioactive decay, we don't ever have 2 reactants. We are definitely going to get a beta particle out of this. I'll do a beta symbol for this one. I'll do an electron symbol for the next one. Now, how many protons does a beta particle have? Maybe a misleading question.
0?
Maybe a misleading question. It isn't a proton. But in addition to this being the proton number, it also is sometimes called the charge. The charge number, or the charge, right? So hydrogen 3 has 1 proton, which also means that in the nucleus it has a charge of +1. So a beta particle, yeah, it doesn't have any protons, but it actually has a proton number of -1. It has the opposite charge of a proton. So we do a proton number of -1. That's important. And then this we called the nucleon number, which also is known as the mass number. A beta particle doesn't have an equivalent mass that a nucleon has. So a beta particle has a proton number of -1 and then a nucleon number of 0. If that's weird to you, then yeah, that's something that you're just going to need to look at a few times in order to remember. All right. So we can simply treat beta decay as, we shoot a beta particle out of the nucleus. We still have the case where our proton number has to be the same on both sides of our arrow, and our mass number has to be the same on both sides of the arrow also. So what do we add to -1 to get a +1? 2. Right. And what do we add to 0 to get 3? 3. All right. And I mean, it's already shown in this diagram, but anything in the universe with 2 protons we call helium, or an alpha particle sometimes, but that's still helium. So if we have tritium undergoing beta decay, we end up shooting a beta particle out of the nucleus and then ending up with helium. So that's the simple version. Let me clue you into the more complete version, and then we'll see if there are follow-up questions about it. So it should strike us as really weird that we are shooting an electron out of the nucleus. There aren't supposed to be electrons in the nucleus, right? So that should strike us as weird. So really what's going on here is that we have a neutron converting into a proton, and then that's what creates the beta particle, right? And actually, let's do our chemical inventory of that to make sure that that makes sense. So if we have a neutron, what is the proton number of a neutron? No, 0. 0. What is the nucleon number of a neutron?
1.
1. All right. So we said the neutron is changing into a proton. What is the proton number of a proton?
1.
1. And what is the nucleon number?
1.
1, right? And then this, well, so we need to conserve our mass. We also need to conserve our charge. So we do have to create something else because as it stands, this doesn't balance, right? We have 0 on this side, 1 on that side, that doesn't balance. So what do we need to add to 1 to get 0?
An electron. Oh,
Negative 1, right? Negative 1. And what do we need to add to 1 to get 1? 0, right? And so yes, this is an electron, which is the same thing as a beta particle. So the more complete story of beta decay is that we have a neutron inside the nucleus that converts to a proton, and in the process ejects an electron, and in the process ejects something called an anti-neutrino, which is kind of like a V with the symbol for that is like a V with a bar over it. Or actually, I don't think it's a V. I have these two little lines here on purpose, and I don't even know what Greek letter that is. It might be the Greek letter nu, but it very well might not be. And we need, and IB says we need to be aware of that anti-neutrino, right? So when we do beta decay, we are going to include the anti-neutrino with our products. Okay? So again, IB says we do need to know about the anti-neutrino, and that happens anytime we have beta decay. So what the heck is an anti-neutrino? It's a tiny particle. When I started teaching IB physics, I said that we weren't real sure if it had mass or not, but I think we're way more sure today that an anti-neutrino does have mass, or neutrino or anti-neutrino. It's just teeny. All right, and again, this is an anti-neutrino. We know about antiparticles, some of us do. Probably, some of us do. So under the, what's it called? The standard model of particle physics. We have particles, and then we have antiparticles, right, which have some identical physical characteristics, and then some opposite characteristics. So an electron has an antiparticle. The antiparticle of an electron has the same mass, right, but opposite charge. What's it called? Yeah, positron. It's called a positron. I'm sure that we've all heard of positrons. Right, so a positron is the antiparticle to an electron. What are other ones we may have heard of? That's definitely the most popular. What?
Antiproton.
Yeah, there certainly is such a thing called an antiproton, but we hear about that far less. A positron is actually a pretty common thing. Isn't there something called, what's it called? PET scan? Is that a thing? A PET scan? PET?
Yeah.
Yeah. Positron emission tomography. So a PET scan uses positrons. We'll get into that a little bit. We'll talk more about that later on in topic 7. So a positron is the antiparticle to an electron, same mass but opposite charge. An antineutrino, and there's 3 different kinds, is the antiparticle to a regular neutrino. All right, other questions at this point about beta decay? I have one other thing to say about beta decay, but I want to see what questions there are first. Yes?
Does a neutrino have charge?
Does a neutrino have charge? I'm pretty sure it does not. In fact, it can't. If it did have charge, then we wouldn't be conserving charge. And this is the whole story. So it can't have charge. There are other physical properties like something called spin and something called color. And it probably has a spin and a color associated with it. I'm not sure. Yeah, Daniel.
Is there like a reason why the antineutrino is there? Or is it just
Well, is there a reason? I'm going to say yes, and I'm going to answer that, but I don't know that I'm going to fully answer it. We have this neutron sitting here. Let's go back to the example we had in the last slide. All right, we have a hydrogen 3, and we have this neutron sitting here. No, one of these neutrons. In fact, it's this one, right? this neutron turns into a proton. And, right, so we have this nucleus sitting here, we don't have a proton there anymore, we have a neutron, and we have this beta particle, this electron, that gets shot out that way. What do we know from maybe December of last year has to happen to this stuff if we shoot some mass off that way? We know. Lauren, what do we know has to happen? Yeah. The electron, so we have this mass, and a piece of it, an electron, gets shot that way. What do we know has to happen to the rest of it as a result of shooting a piece that way? Your hand was up. I didn't pick on you because your hand was up. All right, well, I'm going to stay on you because I feel like you know. Yeah, we have to conserve momentum, right? So if we had no momentum before, and we create some momentum this way, we have to create some momentum that way. And when this has been observed, like quantitatively, I might not get this 100% right, but I'll get it close enough. We didn't conserve momentum. So it's possible that the nucleus, in fact, I don't think the nucleus moves. This thing is in like a lattice structure, right? This can't move, right? It's locked up in a crystal structure of something. So the nucleus doesn't move. So just from a conservation of momentum perspective, we have to shoot something the other way. And the antineutrino is that something. So that might answer your question. I don't think it fully does, but that's at least as fully as I can do it. Yeah?
Where does that electron come from? Is it from like the process of the neutron?
Where does that electron come from? The simple answer, which is the only answer I think I can give you, this is not complete, but it is healthy to think of a proton, to think of a neutron as like a proton and an electron. Not the whole story. Obviously, we have some other stuff because the antineutrino has to come from somewhere, but that's a healthy thing to way to think about it. Cliff, did you have an additional question or input here? Aren't there other types of beta decay? Yeah. So after the questions, there's one other type of beta decay I want to mention. Yeah,
Is
Justin.
that why like neutrons are like slightly?
Is that why neutrons are slightly more massive? I'm going to say yes, and that's definitely a healthy way to think about it, but I think there are other issues at play besides just that explanation. All right, any other questions before I present one additional fourth type of decay that we don't have to know about? All right. So the fourth type that we don't need to know about is called positron decay. And guess what's converting into what with positron decay? I bet you 5 of you. I'm going to wait for 5 of you to raise your hands. What is converting into what? There's like already more than 5 of you. Paul.
A proton to a neutron.
That's exactly right. Yep. So just like a neutron can change into a proton can also change into a neutron. All right. Marker. But let's go through this. This is actually good practice. What is the proton number of a proton? 1. What is the nucleon number of a proton? 1. All right. So we're starting with a proton. We're ending up with a neutron. What's the proton number of the neutron?
0.
0. And what's the nucleon number of the neutron?
1.
Yes. Now, clearly, we need to create something else because not everything's balanced right now. Right? Our mass numbers are quite balanced, 1 and 1, but our charge number is not balanced. So we need to add something else that has to have a charge number of 1, positive 1, and a nucleon number of 0, and that's our positron. Right? That's our positive electron. And then guess what else we make also if we do this? Yeah. A regular neutrino. Right? Not an antineutrino, but a regular neutrino. Alright, so Cliff, is that the other type of beta decay you were alluding to?
They're also
Electron capture, I don't consider, well, electron capture I think is another name for this. If I'm wrong, and we truly do have an electron entering the nucleus to preempt some rearrangement, then that would not be natural radioactive decay. That wouldn't be random and spontaneous. But I think that electron capture is actually another name for this. All right, so that is the full story about beta decay. But again, all you need to be able to do is recognize that for beta decay, we're shooting an electron or a beta particle out of the nucleus. The antineutrino comes along with that, and it's within the realm of possibility. Can't recall if I've ever seen a question about it, but you might need to know that a neutron converts into a proton as part of it. I don't think so. But I would want you to know that. All right, let me catch up here. Let's do one additional example of a beta decay. So at this point, if you don't have your periodic tables out that I gave you, why don't you take those out? All right, carbon-14 is an isotope that I like a lot. We use carbon-14 to date things that aren't all that old, maybe up to 20,000 years old. I like carbon-14. Now, how many protons does carbon-14 have? 6. And the reason we use carbon-14 to date things is that this is pretty radioactive. It's very unstable, and it converts into something else, and it does beta decay to get more stable. So I would like you guys to try, and if we have beta decay, we always have the antineutrino. We don't want to forget about that. I'd like you to complete that reaction and figure out what else we get besides the beta particle and the antineutrino. Right? I don't know that we need foursomes for this. If you want to kind of peek, do it along with the person next to you, that's fine. You're not all done. Another 10 seconds. Robbie, you haven't found it yet. Alright, now most of you are done. So we need a proton number. We need to add something to -1 that gives us 6. I think that's 7, right? Yes. Yeah. And then we need to add something to 0 that gives us 14. I know that's 14. And what do we call an element if it's got 7 protons? Nitrogen. Right. So when carbon-14 decays to get more stable, it turns into nitrogen-14, which is actually regular old nitrogen. That's the standard stable isotope of nitrogen. All right, so that's beta decay. Let's move on to gamma decay. Gamma is the easiest of the bunch. So a gamma ray, not particle, a gamma ray is just electromagnetic radiation. It's just a very high energy photon, a very high frequency photon, right? Very similar to microwaves, X-rays, visible light, right? A gamma ray is just electromagnetic radiation. So